lecture we will continue the discussion that we started in the previous lecture, that is on partial order relations and partially ordered sets. So, a set A along with a relation which is usually denoted by a less than equal sign is said to be a partially ordered set, in short written as a poset, if the relation on A is reflexive, antisymmetric and transitive. We have also seen that if we have a finite partially ordered set, then we can represent it by a diagram called Hasse diagram, which is extremely convenient to visualize a partially ordered set. In this lecture, we continue in the same direction and introduce some special elements in a partially ordered set. So, we have the partially ordered set A less than or equal to, and suppose we have a subset B of A, an element small b belonging to the capital B is said to be the least element of B if B is related to X for all X belonging to the subset capital B of the partially ordered set A. Now, we concentrate on the fact that whether a least element will exist always. So, let us consider a Hasse diagram of this type. Now, suppose this A, B, C, D, E is the set A, and well, suppose the partial order is given by this Hasse diagram. Now, let us consider the set B, which is only E, C and D. Now, we shall see that there is no element in ECD, the set containing ECD, which can be called the least element. If we consider the element C here, of course, C is related to E, which we sometimes just say C is less or equal E, but C has no connection with D. Similarly, D is related to E, this is D over here, but D has no connection to C, and of course, E is only related to E and nothing else. Therefore, this is an example of a subset which does not have a least element. Now, let us take up an example where there are least elements. So, suppose we have a situation like this. Right. So, we have seen this example in the previous lecture. This is essentially the set I 6, which consists of elements from 1 to 6, the integers from 1 to 6, and the partial order is divides, which is denoted by a vertical line. Now, here if we consider the set B as 2, 4, 6, then we note that the element 2 is the least element of this set. 2 belonging to B is the least element of B. Now, we note another fact, that is, if B has a least element, then definitely this least element is unique. We can give a short proof of that. Suppose B has a least element, then that least element has to be unique. We give a proof of this fact. Now, let us suppose, if possible, B has 2 least elements. Suppose B has 2 least elements, small b and small b prime, both belonging to B. Now, by the definition of least element, B must be related to all the elements of capital B. By the definition of least element, B is related to x for all x belonging to capital B. Now, B prime is an element of capital B. Therefore, since B prime belongs to capital B, B is related to B prime. Exactly using the same argument, we can say that B prime being a least element of B, B prime is related to all the elements of B. In particular, B prime is related to B. Now, we can number these two relations that we have obtained. One is B related to B prime, the second one is B prime related to B. Therefore, combining them and remembering that we are after all working on a partially ordered set where the relation is a partial order, that means it is antisymmetric, which means that B prime is equal to B. This proves that we cannot have more than one distinct least elements. Now, this same argument is going to work for greatest elements that we are going to define shortly. So, I will not be doing that proof again, but the argument is going to be the same. So, we have talked about least elements. Now, just like least element, we have the greatest element. So, suppose B is a subset of A, suppose B is a subset of A, an element small b belonging to B is said to be the greatest element of B if x is related to small b for all x belonging to B. Again, by using the same argument as before, we can infer that if greatest element exists, then it has to be unique. So, we do not prove it again, we just write if B has a greatest element then it is unique. Now, just as before, we can have situations where B does not have greatest element or it may have greatest element. So, let us go back again to our example of I 6. So, it is like this. One, 2, 4, 6, 3 and 5. Now, let us try to find out a subset which has a greatest element. Well, if we consider the subset 2, 6, 3, 6 happens to be the greatest element of B. Right. But we can also construct in this same partially ordered set subsets which do not have greatest elements. One such subset is, well, let us write B prime, which is equal to 2, 4 and 6. So, here we are considering this node 2, 4 and 6, and we see that we do not have any greatest element. Now, we move on to the definitions of some more special elements and some special elements which are very typical of a partially ordered set. We define minimal element of a set. Now, in a partially ordered set A subset B has a minimal element if there is an element small b in that subset which does not dominate any other element in that subset. Now, let me write down the definition. So, suppose B is a subset of A. An element small b belonging to capital B is said to be a minimal element of B if x less or equal B and x not equal to B together. Okay, we have to remember that x, of course, B is less or equal B. So, we do not take that case. So, we take the cases where x less or equal to B and x not equal to B, and we say that this should not happen. So, if x less or equal B, that is x related to B and x not equal to B, now here we write in short x strict less B for no x belonging to capital B. So, this means that there is no x other than B inside the subset capital B which is related to the element small b. We can define maximal element of a subset in the same way. So, I write down maximal element well, just to avoid any confusion, let me change the name of the element. So, I write U, an element U belonging to capital B is said to be a maximal element of B if B strictless X for no X belonging to B, that is B is not dominated by any other element of the set B. Well, what we must understand here is that there is a difference between minimal element, maximal element, least element and greatest element. Now, what is that? For example, let us look at again the lattice that we considered again the Hasse diagram that we considered just in the before. So, I draw the Hasse diagram again. So, here we have 4, 2 going to 1 and then 6, 3 going to 1, we have 5. So, we numbered them. This is exactly what I drew above. All right. So, now let us consider the set B prime that we again considered before, B prime which is 2, 4, 6. We saw that this set does not have a greatest element, of course, because there is no element which such that all the elements in B is related to that element, but the two elements 4 and 6 are maximal elements of the set B prime. That is because there is no element in the set B prime such that 4 or 6 is related to that element. So, it is a maximal element. So, we can write that 4, 6 are maximal elements of B prime. Now, we see that B prime has a least element. It is of course a unique element, and that is 2. 2 is the least element in B prime. All right, and 2 is of course a minimal element, because there is no element other than 2 which is related to 2 inside B, inside B prime. Thus, we have seen the ideas of least element, greatest element, minimal element and maximal element for subset in a partially ordered set. Now, we shall move on to another idea, which is the idea of bounds. Now, our starting point is again a lattice. Our starting point is again a partially ordered set with a partial order. And we also consider a subset B in A. Now, the question is that what do we mean when we say that an element L, small l, is a lower bound of B in A? That is precisely this: an element L belonging to A is said to be a lower bound of B. You can add in A if L is related to all x belonging to B. Now, we consider the set of all lower bounds of the set B. Now, these lower bounds may or may not belong to the subset capital B, but of course, they have to belong to A. So, consider this set of all lower bounds of B. Now, how do we name this set? Let us call this set L subscript B, which is of course a subset of A. Now, we will consider the case when L sub B has a greatest element. In case L sub B has a greatest element, the greatest element of L sub B is said to be the greatest lower bound of B in A, of course. The greatest lower bound of B is the greatest element of L sub B. Now, exactly in the same way we can define upper bounds and least upper bounds. We do that. An element U belonging to A is said to be an upper bound of B, of course in A, if x is related to u for all x belonging to B. Here also we should write for all x. Now, suppose u B is the set of all upper bounds of B then in case this set of upper bounds has a least element, we call that element the least upper bound. So, we write the least element of u B in case it exists is said to be the least upper bound of B. Now, there are some short forms. We will be writing the greatest lower bound of B simply as GLB B the greatest lower bound of B and the least upper bound of B will be written as LUB of B the least upper bound of B. Now, we will consider, we can consider some lattices, particularly we can look at some Hasse diagrams of lattices and check least upper bounds and greatest lower bounds of certain subsets. Now, for example, if we consider a lattice of this type, let us take this example. All right, and let us name the points, possibly let us name this as A, then B, C, D, E, then F, G and H. all right. Now, if we consider the subset F C G, let us call this B, then we will see that we have got two lower bounds of this set, namely C and A, because C is over here. C is of course less or equal C, C is less or equal F, C is less or equal G, and A is less or equal to C. A, because it is connected to F through a path, F is A is less or equal F, A is less or equal to G. Therefore, both are lower bounds. So, this is the set L B, the set of lower bounds of B, and among this set we see that we have the element C such that C is less or equal C and C is less or equal to A. So, C is the greatest element of L B. C is the greatest element of L B, and so we can write that the greatest lower bound of B is equal to C. Now, the question is that does this set have a least upper bound? For that we have to first try to find out the set of upper bounds. My set contains the nodes C, F, G. Now, we see that the element H is such that F is less or equal H, G is less or equal H, and so is C. Therefore, the set H is U B, the set of upper bounds of B, and since it is a singleton set, this itself is the least upper bound of B. Now, we come to a question that is it possible to have a partially ordered set and a subset inside that partially ordered set which has lower bounds, but no greatest lower bound, and we can invert the question and replace lower by upper and say that is it possible to have subsets in a partially ordered set which has upper bounds, but no least upper bound. Now, the answer is yes. Let us look at a Hasse diagram of a possible partially ordered set. Suppose we have 4 points, we name the points as A, B, C and D, and suppose we write like this. So, I have drawn a Hasse diagram, we see that the totality is ABCD, and let us consider the subset B, which is equal to CD. Now, if we try to construct L sub B, we will see that L sub B consists of 2 points A and B, because A is less or equal C, A is less or equal D, B is also less or equal C, B is less or equal D. Okay. Therefore, both of them are lower bounds of CD. But which one is the greatest lower bound? The answer is there is no greatest lower bound. The reason is that the elements A and B are not comparable. Now, this leads us to a particular question. We would like to construct partially ordered sets such that some specific subsets of that partially ordered set will have some properties related to greatest lower bound and least upper bounds. Now, one definition has proved to be very useful, that is the definition of a particular class of partially ordered set called lattices. Suppose L with a partial order less or equal is a poset. Now, this L will be called a lattice if given any two elements, of course not necessarily distinct, will be able to find a least upper bound and a greatest lower bound of that subset. So, suppose the elements are same, suppose I consider an element x belonging to L, and of course, I consider another element y belonging to L and then construct the set x y. What I say is that this set x y will always have a least upper bound and a greatest lower bound. All right. So, this makes a lattice. Now, the question is that do we have examples of lattices? The answer is yes. So, first example that comes to my mind is the example that we construct by taking the power set of the set 1 to 3, the Hasse diagram corresponding to the poset defined by using the set subset equal relation is this. So, we have the null set phi at the very bottom, then 1 we connect it, then this we will write 2 here, then this is 3, we will write 3 here, then this is 1 2, this is 1 3, and this is 2 3. These are the subsets of S, and eventually we have 1 2 3. We join this as well. Now, pick up any two elements from this lattice, which is essentially the power set of S. If we pick any 2 elements, they are basically subsets of S, and suppose we write them as A B. What we can find is that greatest lower bound of A B is simply the subset A intersection B, which is of course an element of P S, and least upper bound of A B is A union B, which is an element of P S. Thus, this is a lattice. We can take up another example of a lattice. Let us look at that. So, let us consider something like this. Or like this. These are also lattices. Let us name them A, B, C, D, E, and A, B, C, D, and E. What you can do is that you can pick up any 2 elements, and you will see that you will be able to construct a greatest lower bound and a least upper bound of that set. There are some differences between the lattices that we the first lattice that we saw and these ones. These differences will be discussed in the next lecture, but I will stop this lecture by introducing another concept related to lattices. What we find is that this idea of greatest lower bound and least upper bound, and the fact that any subset containing 2 elements in a lattice will always have a greatest lower bound and a least upper bound leads us to define some kind of binary operation of on lattices. For example, suppose we start with L with this, and suppose that it is a lattice. Suppose L is a lattice, then take two elements in L. In this case, these two elements do not have to be distinct. What I will do is that if they are distinct, then I will define x, this y, this symbol that I draw will be called disjunction all right. X disjunction y will be nothing but least upper bound of the set x comma y in case x is not equal to y. In case x equal to y, I will simply define x disjunction y as x, which is basically x disjunction x. So, this is the case x equal to y. I could have written y also. Similarly, I define x conjunction y as greatest lower bound of the set x y when x is not equal to y and well equal to x, or you could write y as well in case x equal to y, and this symbol is called conjunction. Now, we can consider a lattice along with the partial order defined on it, some kind of algebraic system having these two operations, conjunction and disjunction. So, I can write the whole setup as L, then the partial order, then the disjunction and the conjunction. This is for today's lecture. In the next lecture, we will build algebraic systems on this setup. So, for the time being I stop. Thank you.